All right, let's just jump right in. Organic chemistry, it can feel like trying to learn some impossible secret language, right? Full of these bizarre names for really tangled up structures. But what if I told you it's not about memorization? It's really just a logical puzzle, a secret code. And in the next few minutes, we're going to crack it together.
Okay, so take a look at this thing. We've got a double bond and a triple bond. At first glance, it just looks like a total mess. So where do you even start? Which end gets to be carbon number 1? This is the exact kind of puzzle that trips people up all the time. But the solution? It's surprisingly elegant.
And that is the secret sauce right there. This whole thing, it's not about memorizing a billion different names. It's about learning a system of rules, a hierarchy. Once you know who has priority, naming becomes a pretty simple step-by-step process.
So let's get back to our little puzzle molecule. We've got two features basically fighting for the spotlight. The double bond, which makes this an alkene, and the triple bond, which makes it an alkyne. They're battling for control over the numbering. So who wins?
This brings us to our very first rule of engagement. When you've got both alkenes and alkynes in the mix, there's a really clear system for deciding who gets top billing.
Okay, so the first rule is super simple. It's all about who's closer to the end of the line. You just start counting from whichever end is closer to any multiple bond. Doesn't matter if it's double or triple. If that triple bond is at position 1 and the double is at position 2, well, the triple bond wins. It's all about snagging the lowest number possible for that first interesting spot.
Okay, fine. But what happens if it's a perfect tie? Let's say the double bond is 1 carbon in from the left and the triple bond is 1 carbon in from the right. Now what do you do?
And here it is, our crucial tiebreaker. The official rules give the double bond just a little bit of an edge. If they're symmetrically placed, you start numbering from the end closest to the double bond. That ensures it gets the lowest possible number. Game over.
Okay, so now how do we actually build the name? It's pretty cool, actually. Once you've got the chain numbered, the name for the double bond, the ene part, always comes before the name for the triple bond, the yne part. And check out step 3. This is a neat little detail. To make it sound better and avoid that awkward vowel clash, you drop the e from ene, so it becomes einine, not ein. It's like a tiny grammar rule, but for chemistry.
All right, feeling good? You think you've got this down? Double versus triple bonds, tiebreakers? Seems easy enough, right? Well, hold on, because now we're going to throw in a plot twist. Let's add a functional group into the mix and watch how it completely changes the entire game.
Let's introduce an alcohol group. The second, and I mean the second, this OH group shows up on the molecule, all those rules we just carefully learned about double and triple bonds, yeah, you can just toss them right out the window. They have zero power now. The alcohol is the VIP in the room, and the numbering has to start from the end closest to it. No questions asked.
And this brings up a really, really common mistake people make. If you call a 4-carbon alcohol but2-ol, that's actually wrong. And here's why. Think about it. We use ane to signal a double bond, right? So if the main carbon chain is all single bonds, we need a way to signal that, too. And that's exactly what the ane does. The correct name is but-an-2-ol. That an is a little message that tells you the backbone is a plain old alkane.
So we know an alcohol outranks a double bond. But what happens when you have more than one of these so-called VIP functional groups in the same molecule? Well, this is where we need the ultimate priority list, the full hierarchy.
Let's cook up a new puzzle. Imagine a molecule that has both the ketone group and an alcohol group. Who's the bigger VIP now? Who gets to define the name and the numbering when you have two heavy hitters in the same rin?
So this chart basically lays out the pecking order. And as you can see, clear as day, the ketone has higher priority than the alcohol. Now, here's the absolute key. Only the top dog, the highest priority group, gets to define the name's suffix. Every other group, no matter how important it seemed a minute ago, gets demoted. It just becomes a prefix, a simple descriptive tag on the front of the name.
You gotta love this analogy. It's perfect. As soon as that ketone shows up, the once mighty alcohol group, the one that used to call all the shots, is totally demoted. It loses its fancy ol suffix status and just becomes a prefix, hydroxy. It's like it goes from being the king to just another face in the crowd, listed alphabetically with everything else. What a fall from grace, huh?
Okay, we now have all the tools in our belt. We know about proximity, we know about tiebreakers, we know about VIPs, and we have the ultimate priority list. It's time. Let's put it all together and solve one final complex puzzle.
Okay, take a good look at this one. We've got our high-priority ketone, our now demoted alcohol, and just a simple little methyl group hanging out. Let's use our system, our rules, to name this thing properly, step by step.
All right, let's just walk through this. Step 1, find the VIP. That's the ketone, no doubt. So, we know the name is going to end in -one. Step 2, number the chain. You got to start from the end that's closest to our VIP, the ketone. Step 3, name the commoners. The alcohol is now just hydroxy, and the methyl group is, well, methyl. And the final step, step 4, you put those prefixes in alphabetical order. H for hydroxy comes way before M for methyl. Simple as that.
And when we put all those pieces together in exactly the right order, following all of our rules, we get the final name 4-hydroxy-2-methylhexene-3-1. See? No guesswork, no flashcards, just pure, simple logic. You just crack the code. How cool is that?
So, here it is, your new toolkit for naming these things. It all just boils down to a hierarchy, a priority list. Functional groups are the kings. Then you've got your double and triple bonds. The highest priority group gets to be the suffix, the grand finale of the name. Everything else, it just becomes a prefix. And you always alphabetize those prefixes. That's pretty much the core logic of the whole system.
So think about what we just did. By learning a system of logic, instead of just trying to memorize a bunch of random facts, you've actually learned to read a language that describes the very building blocks of our world. Kind of makes you wonder, doesn't it? What other complex systems are out there, just waiting for someone like you to come along and decode their language?